Hello! Now we are going to pick up with Charles's law. First we talked about Boyle's law, that pressure and volume are inversely proportional, so when one goes up, the other goes down. For example, I have this massive syringe thing. This is actually not used for medicine or anything, it's just for doing gas law demos with. But anywho, so at this point right now, it's got 130 milliliters of air in it, okay, and it used to have a valve that closed here, but I don't know where that ran off to. If I apply more pressure, which is harder than it looks, okay, the volume decreases, okay, but there's more pressure in here now. So the more you decrease the volume, the higher the pressure goes up. And you can kind of hear it, that pressure releasing once I move my hand out of the way. All right, now we have Charles's law, which is the temperature-volume relationship. We've seen everyday applications of this. The hot air balloons would be one. Gases expand when they're heated. I left balloons in the car in August for my son's first birthday, and they popped because gases expand when they're heated. So Charles's law states that the volume of a fixed quantity of gas, meaning the container's like sealed in such a way that there's no more moles entering or exiting the gas, it's a fixed quantity, at constant pressure is directly proportional to its absolute temperature. Volume is directly proportional to temperature at constant pressure and constant number of moles. Well, you may think it's hard to keep a gas at constant pressure, but it's not really. As long as you have your gas are in an open container that's open to the atmosphere, then your gas is always at 1 atm of pressure. So when we do some of our experiments in the lab, we'll be able to know what the pressure of our gas was without actually measuring it. We'll just, from the pressure in the room, that's also the pressure of our gas. So constant pressure isn't as hard to achieve as it sounds. All right, so Charles's law, temperature and volume are directly proportional, meaning when one goes up, so does the other one. All right. Now, oh, wait a minute. Why does that cause hot air balloons to float? Well, as the gas expands in the hot air balloon from the heat, well, this is not a fixed quantity of gas, okay? This is open. Come back, cursor. This is all open, so molecules of gas can escape. So as the gas is heated, the molecules expand, trying to take up more room, and they exit, okay, out the opening in the hot air balloon. Therefore, you end up with less gas inside the balloon than you do outside, meaning your balloon is less dense than the air around it, so it floats. All right, so here's a graph of what Charles's law looks like. Boyle's law was inversely proportional, so we saw a hyperbola. Now this time we see a straight line because this is what directly proportional looks like. The formula then, instead of multiplying our two variables like we do with an inversely proportional relationship, we divide by them since it's directly proportional. So V1 divided by T1 is equal to V2 divided by T2. In order for this to work, though, the temperature has to be in Kelvin. Okay, these two have to be, in order for this relationship to be drawn, your temperature has to be in Kelvin, or you won't get the right answer. All right, so that's Charles's law. And remember, just to convert to Kelvin, just add 273. I seldom mess with the 0.15 because the 273 already has us at 4 sig, or I can't even count, already has us at 3 sig figs anyway. So when we plug it in here, chances are we're only going to have 3 significant figures in our volumes anyway. So just kind of play that one by ear and decide whether or not you need to include the decimal point. Hold on a moment. All right, so that's Charles's law. Here is a pictorial version of Charles's law. We started out with our plain old balloon at room temperature, and in the second picture they have poured liquid nitrogen on it, which is very cold, dropping the temperature very quickly, and that causes the, thank you Lucas, that causes the volume to drop. Okay, temperature and volume are directly proportional.
Excuse me.
Now, do we have a constant number of moles here? Yes, the balloon is sealed, so there's so many moles of air in there. So moles are constant. Pressure is also constant because we're at room pressure. So when we lowered the temperature, volume decreased.
Oh.
All right, so assuming pressure is held constant, to what volume will a balloon initially at 1 liter change if its temperature is decreased from 300 to 75 Kelvin? So just like this balloon example, we start out at 300 Kelvin and we decrease the temperature to 75 Kelvin. Okay, we have a 1 liter balloon. Is it going to go up to 4 liters? Okay, no, they're directly proportional. When one goes down, so will the other. Okay, so if we lower the temperature, the 1 liter balloon is definitely not going to expand by a factor of 4 or by a factor of 2. We're getting it cold, so it's going to shrink. Our other option is that it stays the same. That's obviously out. So if we were to plug it in our calculator, we would know that it's going to go down to 0.25 liters. Or we can just tell by process of elimination here. So the final volume will be quite a bit less than the initial. All right, now for our next law, Avogadro's law. Avogadro's number is the number of particles in a mole. So this one's pretty easy to remember that Avogadro's law has to do with the number of moles of gas. But first, before we get into that one, we'll talk about this other one briefly. Gay-Lussac's law of combining volumes. 2 scientists there discovered that at a given temperature and pressure, the volumes of gases that react with one another are ratios of small whole numbers. Now, that doesn't sound that earth-shattering to us because we know that already. We know that for every 2 moles of hydrogen gas, we're going to need 1 mole of oxygen gas, and that will form 2 moles of water. Back then, though, that was a big deal, okay? They did not have balanced equations and chemical formulas and all that yet. They just messed around with gases and weighed them before they reacted and weighed the resulting mixture, and they basically figured out stoichiometry. All right, now Avogadro took it a step further and went so far as to say, if we have equal volumes of gases at the same temperature and pressure, not only will they react with one another in whole number ratios, I think they've got the same number of molecules in them. So if I have a liter of nitrogen gas at the same temperature and pressure as a liter of oxygen gas, I think they have the same number of molecules. Okay, that led to the concept of a mole. 1 mole is 6.022 times 10 to the 23rd molecules. Now, we call it Avogadro's number because it's based on his hypothesis, but he did not actually do the math and come up with the 6 times 10 to the 23rd business, though. It's just the idea behind it is his. So that's now Avogadro's law. The volume of a gas at a given temperature and pressure is directly proportional to the number of moles of gas. This isn't that surprising, okay? If you put more moles of gas in the balloon, guess what the balloon's going to do? It's going to get bigger, okay? The volume will increase. So all of these are, as I said, a lot of common sense relationships that we know already. Put more air in your tire gets bigger to a certain point until the tire can't stretch anymore or the balloon can't stretch anymore. And then, like, let's say the volume of the balloon has gotten as big as it possibly can. What if you keep putting more moles in it? Well, then the pressure in the balloon is not going to be the same as the pressure outside the balloon. Our pressure will no longer be constant. And then once you get more pressure inside the balloon than you have outside, pop. Okay, so until that balloon pops, though, even though you're putting more and more moles of air into that balloon, the pressure inside that balloon is the same as the pressure out here. So if it's 1 atm here, the pressure in the balloon's at 1 atm. Okay, until the balloon can't stretch anymore, then once the pressure goes over 1 atm, it'll pop. So more moles equals more volume to a point, okay, until the container can't stretch anymore. Now, all this being said, temperature and pressure have to be constant in order for Avogadro's law to work. All right, so here is an example, kind of a pictorial representation of Avogadro's law. And you guys know this number already. We can show that 22.4 liters of any gas, if we've got it at 0 Celsius and 1 atmosphere of pressure, has 6 times 10 to the 23rd gas molecules in it. So whether it's helium or nitrogen or methane, doesn't matter, any gas if it's at standard temperature and pressure. Standard temperature and pressure is not room temperature and pressure. Okay, the pressure is about average, 1 atm, but we don't really hang out at 0 Celsius usually. But that is what STP is, at a very cold temperature, 273 Kelvin or 0 Celsius, and a pressure of 1 atm. Now, all three of these gases, if we have the same temperature and pressure, they have the same number of molecules in there, and therefore the same number of moles, 1 mole to be exact. However, they all have different masses. Okay, the nitrogen is going to be a heavier, more dense gas than the helium, which is the lightest, and then methane's in the middle. Okay, so we can use the molar mass to deduce the density here. So the helium will float, whereas the nitrogen will not. Methane, not sure. I'd have to look up the density of just regular air real quick. All right, so that's Avogadro's law. Now, here is a problem we will go through in class. And it's still going. And we're still going. Okay, now remember that PTV trick I did with the paper that you rotated? Wish I had it here, but we'll just pretend. Remember, they go in alphabetical order, P, then T, then V. And then you just stab a pencil in whatever variable you are wanting to keep constant, and then rotate pressure up or down, or whatever it is you're wanting to change, and you can see how the other variables will react. So, in a situation like this, you're going to mathematically calculate it, of course, but first, you can kind of estimate what your answer should be. So here we have a gas at 30 degrees Celsius and 1 atm, and we have a volume of 0.8 liters. What's the new volume going to be for the gas at 60 degrees Celsius and 1 atm? Well, our first thought may be, what law should I use? Okay. Well, we changed the temperature. We took the temperature up from 30 degrees to 60 degrees, so we got it hotter. And we're asked what's going to happen to the volume. It starts out at 0.8. What's it going to be once I double the temperature? Well, what about the pressure? Well, it doesn't change. It just mentioned that to trick you up. It's a constant pressure, so pressure isn't changing here. So we can use the volume temperature law, the hot air balloon one, Charles. All right, so using just our common knowledge, what's going to happen when you heat up a gas? Its volume's going to increase. So we know the result of that before we even type in any numbers into our calculator. Same thing here. A gas which has a pressure of 1.3 atm occupies a volume of 27 liters. What volume will it have if the pressure is increased from 3.9 atms at constant temperature? So in this one, we are tripling the pressure. Okay, what's going to happen to the volume? We're going to squeeze on the gas with 3 times as much pressure. So the volume's going to go, according to Boyle's law, they're indirectly proportional. When pressure goes up, volume goes down. So if our pressure goes up by 3-fold, our volume's going to go down by 3-fold. Whoops, my bad. And so the 27 liters will become 9 liters. So those are the easy ones where we're just changing 2 variables at a time. In real life, however, it's quite common to not be able to keep all the variables constant except for 2. And so if you have temperature and pressure and number of moles all changing at once, there is a way to do that, and that is using the ideal gas law. PV equals nRT, or PERVNERT, as I call it, which I know sounds stupid, but it makes you remember it. So that'll be coming up next. Aren't you looking forward to it?
That's